Hello everyone and welcome to the 39th lecture of the course Advanced Structural Analysis. We have discussed the basic concepts of the plane frame in the last session. We implemented it in a manner such that the computer code related to the similar process can be prepared, and then we also looked at one problem which was solved using the standard stiffness approach, which is suitable for the computer implementation in the last session. Now, in this session we will be moving ahead with the implementation of the similar stiffness approach to the grid structures. The content which is defined over here is very similar to the plane frame system which we did. We will in fact see that there is a very much similarity between the plane frame and the grid structures. So, the steps related to the assembly, the steps related to the rearrangement as well as the solution are more or less same. So, in fact, that remains largely a kind of an advantage with the method, that once you are comfortable with the stiffness evaluation for the individual member components in the local coordinates, and you are able to make the transition from the local to the global coordinates of the given system, the remaining part of the process of assembling the overall stiffness as well as the load vectors, the evaluation of the system for the rearrangement part, and finally the solution of the given system, they largely remain same for all the different methods. So, what necessarily changes is the part of the standard metrics of the individual members, and then the somewhere a small difference with respect to the rotation matrix which is defined for the given cases. So, our emphasis in this case will be to identify the basic difference between a plane frame and the grid system, and once we are comfortable with that, we will briefly see that the method is more or less similar the way we identify for the plane frame system. Moving ahead with this part of the course, we will also see that much of the content which we are discussing now onward is very specific to the computer implementation of the given matrix approach. Now, this content cannot be done manually for a larger system, because even in a simplistic system, the manner we are seeing here, 3 number of nodes or 4 number of nodes, we end up with say 12 or 9 number of degrees of freedom. So, eventually you will have a system where say 4 cross 4 or minimum 6 cross 6 kind of a systems of the stiffness will appear in the given cases which are to be solved. Now, these cannot be done manually. So, one must also understand that taking up these problems or taking up the real structural analysis of the given system without the computing algorithms or without the help of a system which can do the calculation for the larger systems is not very much possible. Okay. So, we have the approximate methods, but those are having their own limitations. So, in order to know the standard approach of the matrix analysis, one must get a bit comfortable with the analysis of the given system in the computer program. The method of the system which we have discussed up to now is based upon a simple MATLAB algorithms. MATLAB in general is a very simplistic programming language which is more like a computational tool, computational mathematical tool. We do not need much of the syntax burden in the system. So, you can easily go ahead with the writing your statements and the algorithms. A very simplistic set of some lectures as well as the tutorials are provided in the MATLAB link which is available in the course panel. So, you are expected to go through it and be little comfortable with the MATLAB part, because using this computational tool solving these problems become much more easier. At the same time, the content as we move ahead with the space structures is also something which is typically not covered largely. So, you have to refer some books also, because there is a limitation which can be covered during the classes. So, as we discuss the basic concept, you again go through it, try to recall it, try to see that what is the overall intention of the part of the lecture which is being provided, and with that if you will give sufficient time, you will be able to understand. So, at the very beginning, some of the times the concept may appear to you which are not very easy to go ahead with, but as the efforts will be given, of course, the content can be easily understood. So, now moving back to the given system, the grid structures are very similar to the plane frame, as we consider that in a given system that both are like a plane structures, the members are in a given plane only. Only difference lies that the loading is either in the same plane, so we call it as a plane frame, but if the loading is not in the same plane of the members, we call it as a grid. Okay. So, typically if you see like a simple member, like if I define in this case the coordinate system which is located with the x, y and z in the given problem, one can just come up with say a system like a plane frame in this manner, right. So, when I say plane frame, it typically means that the given members are located into this coordinate system. So, members are only in this plane and the loading which is provided in the system is also in the same plane. So, at any point of time the out of plane direction, which is the third direction of the given system, is not going to interact with the geometrical dimensions of the given system as far as the loadings as well as or the member dimensions are concerned. Everything is defined in the same plane on which the given frame is located. At the same time, when I now come up with the grid as a structure, we consider this like this system. So, this is a member which is now located in the xy plane. So, you can consider that this is the direction along x, this is the direction along y, and normal to the given plane is the z of the given system. If the visualization is not very much clear over here, I will just try to draw it in a manner such that the 3D representation can be thought about. So, this is like the member 1 which is drawn in the direction x, whereas the second member which is over here is along the direction y of the given system. So, this is the second member. In the same manner, if I consider the third member, this is again the member which is located with respect to the given axis. So, which is again in the direction x of the given system only. So, at any point the loading which is active on the given system is along the direction z. Okay. So, as a simplistic example, if you want to consider, it is a simple hand, like if I just put in this manner. So, this is one of the member, this is the second member, both are in one of the plane, which is say the plane of the given system. And if I put a load which is applied from the top on the given system, so this load is appearing normal to the given plane, which is the plane of the given members. So, as a simple idea, when we consider the frame, if I consider this as a arrangement of the frame, I have to apply the loading which is also in the same plane. So, loading in this manner could be active, loading in this manner could be active, but any of the load which is normal to the plane is not active. So, that may not be considered for a frame cases, but when we come to the grid, we consider that the loading is active on the system which is normal to the plane of the members. So, if the member are defined in the xy plane of the system, then the loading is active in the z direction of the given system. So, this is one of the basic difference, that the grid system is similar to the plane frame, that members are defined always in one plane only. When it comes to the forces, forces are applied in the same plane when it comes to the plane frame systems, whereas in the grid systems the forces are normal to the plane of the members. So, the grid members, if they are in the xy plane, the forces are applied in the z direction. The third thing is about the moment. Now, if we consider this plane frame system, how do we define the moment direction? We typically say that the member will bend in this manner, right, or member will have the bending in such a manner that it is defined as a rotation about the axis z. So, if this is a plane like a face of the given system, so at any point of time the bending will be located with respect to the normal to the given system. So, of course, dimensions are not extending in the direction z, but the moment or the rotation of the system is taking place about the axis z. Okay. So, that is why we typically describe the degrees of freedom in the given system at any point in a frame system as the translation along x, translation along y, and the rotation about the axis z, which is shown by the double headed arrow in the z direction, which means that the axis which is normal to the given plane is the plane of the rotation, or the moment normal is defined in the plane which is the given plane of the members. Normal to that we have the moment vector. So, when we come to the grid system, we can, so this is what we do with the plane frames, that moment in the plane frame have the moment vector normal to the plane frame, which means that if this is the xy plane of the frame members, the moment vector will be in the direction of the z in the given system, and that is very natural. If you have your member like this, it will bend in this manner. So, this is about the axis z, which is the bending taking place on the given system. Whereas, in the grid system, as you are considering your systems to bend also, because due to the vertical loads which are active in the direction normal to the plane of the grid, the members will bend also. So, how the bending will take place? Like this member, if I talk about, this member will bend like this, something like in this manner. Right. So, at any point if I consider that this member is bending in this manner, so the plane of the bending, the way it is taking place, the rotation of the system, and I now define the moment vector of the system, I realize that the moment vector will be in the same plane, it is along the direction y of the given system. So, if it is the member which was aligned along the direction x and that is bending, the moment vector on the system is about the axis y of the given problem. Similarly, if this was the second member which was aligned along the direction y, if this will bend at any point, say it has a bending like this. So, this bending direction will be defined with respect to this moment vector, and that is the direction along the x. So, the moment vectors are in the same plane when we typically define the grid system. So, that is a very simplistic idea that if you have a grid as this member, it will bend of course with respect to the transverse load which is applied, but all the members of the grid are in the same plane. So, that is why the direction of the moment is actually in the same plane of the given system. Whereas, when we talk about the plane frame of the system, the member, if it is defined in this given plane or the vertical plane, the loading has to be also active on the same plane of the system. Okay. So, this is a primary difference which we must understand in terms of the grid and the frame system. Once we are comfortable with this part, we understand that at any point the frame system will have the 3 degrees of freedom or the 3 major displacements. One is the translation about the normal directions, which is the normal to the given plane. If the plane is the xy plane for the given grid system, so the transverse to that the member will bend in the given system. So, if I say that along the direction of the x, along the direction of the y and along the direction of the z, there are 3 displacements u, v and w identified. So, the displacement which the grid system will actually take is actually about the transverse direction w of the given system. I think that is very natural. If you apply a grid system and somewhere you apply the load on the in the direction of the z, the displacement is supposed to take place in the z direction, right. So, that is the w displacement of the given system. So, this is one of the possible displacement which we typically get in a given system. So, we consider that in a given member of a plane frame, grid system. If we consider this as a grid system and this is say one of the length direction of the given member, say I define it as a x of m, the in plane direction, because grids are in a generally plane of the given system. So, say this is the ym direction of the given system and say this is the zm, the normal direction of the given system. So, the displacement which we define at any point is typically in the direction of z of the given system. So, this is delta z which we typically describe at any node one of the displacement in the transverse direction of the given plane. The second is the moment, and that moment is like a twisting moment of the given system, and that we call as the given moment in the x plane. So, now one can consider it in a very simplistic manner from the previous figure, as we already said that both the members are going to bend. If this member which is aligned along the direction of the x is going to bend, so its bending is about the axis y because in the same plane. Similarly, this member which is aligned along the direction of the y is going to bend, so its bending will be about the axis x of the given system. So, that means the system of the grid is going to take the moments in both the directions of x and y, as x and y is the in plane of the given grid system. So, that is why we typically say that there will be 2 moments which will exist in the given system. One will be the moment about the direction x or the axis x, and second will be the moment about the axis y of the given system. Now, of course, if the member is aligned in the x direction itself, the first moment will become the twisting of the given system, whereas the second moment will become the flexural moment of the given system. Okay. So, this is a very simplistic idea now to consider the possible degrees of freedom in a grid system. We have one which is the delta with respect to the z direction. We have the second which is theta with respect to the axis x of the given problem, and then we have theta with respect to the axis y of the given problem. So, these are the primarily 3 set of possible displacements which we consider in a grid system. If you consider that extension is also possible in the given length, then we also add delta with respect to the direction x or the extensional deformation in the system. But in most of the cases, as we will consider that the member lengths are not changing, members are not extensible. So, we go with these 3 primary set of displacement parameters of the given system. So, using these ideas we get to realize that in a grid system these are the typical arrangement of the degrees of freedom, that this is the x of m, the normal the length along the member coordinate. This is the in plane coordinates of the grid system, which is yf, ym, which is in the same plane, and this is the normal to the given plane of the grid, which is the zm direction. These are all defined in the local member coordinates. Now, corresponding to these three, we get the 3 degrees of freedom at the joint 1 and the joint 2 of the given system. So, at the joint 1 we have the first one, which is located with respect to the moment on the given system. Second one is also defined with respect to the moment in the second direction, and the third one is defined with respect to the translation in the given system. Of course, now this question of that why did we number them as 1, 2, 3 in this manner, not say the transverse displacement being 1, the other two being 2 and 3, you will see very briefly that what is the reason for selecting the numbering system in this manner. But the idea is that at any point of a grid system we are supposed to get a translation in the vertical direction normal to the given plane of the grid, and two possible moments which are in the direction of the grid system. So, if the grid is in the xy direction, the direction of the moment about x axis, about y axis will be there, and the translation in the z direction will be available. So, these are the three possible set of degrees of freedom which we get at any point of the system. Considering the two nodes, we get these 6 total degrees of freedom in the given system. Now, as a first point of the system, how do we define these possible changes which are taking place in the system? So, as we located this as a global axis, so global axis means we have this x, y and z which are globally defined for the given structural system, whereas in the individual member coordinates we could have the member axis also. So, if I go to the member axis, we have defined like this, that individual in the directions of the member, these are the possible set of degrees of freedom which are located as 1, 2 and 3, 4, 5 and 6 in the given system. Now, what we also need, we need a translation between these local or the member coordinate system to the global system, which is defined for, say, if I just go with the same case in the global system. So, along the direction x there will be one moment, along the direction y there will be the second moment, and then along the direction z there will be the one translation. Similarly, at the node 2 also, which is corresponding to the degrees of freedom 4, 5 and 6, we will have one moment about the axis x, one moment about the axis y, and one translation about the axis z of the given system. So, how do we convert now the individual degrees of freedom or the forces which are in the direction of the local member coordinate to the global coordinate? That is our next aspect. At the same time, what we must also realize that in the local coordinate, when we are defining the given system, the one moment which is defined in the local member direction is the twisting moment. So, this is typically responsible for twisting in the given system, whereas the second one which is normal to the given plane, the given length or the axial length of the given member, is actually going to make the system bend. So, that is the flexural of the given system. So, one can consider that if this is the member of the grid, there is one moment which is in the direction x which is trying to twist the given member, whereas if this is the grid plane, there is second moment which is now active with respect to this direction. So, what it will try to do? It will try to bend the given system. So, this is the second idea. So, when we are trying to locate the bending moment with respect to the given system, we are actually locating the second moment of area about the same axis about which we are locating, about which we are defining the moment, and that is the axis y. So, the expression which we will define subsequently in the stiffness part will have the contribution of I of y to describe the second moment of area for the given system. Okay. So, with this idea in mind, we realize that now at any given point or any given member, there are two joints, say the joint j and the joint k. At both the joints we get 3 degrees of freedom each. The two moment degrees of freedom or the rotations of the given system, and one translation in the vertical direction. With this idea in mind, now we can go ahead with the calculations of the stiffness matrix of the system in the given problem. So, as we define the analysis steps will remain same. Identify the input parameter, identify the stiffness and the load vector for the individual member part in the global directions, assemble the overall load vector as well as the member stiffness, and rearrange the given matrix as per the restraint and the free degrees of freedom, obtain the solution of the given system, and then do the post computation enhancement. Typically, the post computation means that we are just going to evaluate the response of the member forces and the reaction forces of the given system. As an input parameter, we realize that we have a system which is very similar to like this. We can define the node numbers, the x coordinate and the y coordinate. Why we only need the x and y coordinate? Because the member is in a 2D plane only. The z direction is a loading direction, but in general all the points of the system will be at a common z axis. So that is why there is no need to define the z coordinate of the given system. Now when it comes to the restraint degrees of freedom, we realize that at any point we have one translation which is along the z direction, which is in the transverse direction of the given system. So that is one degree of freedom which we need to define restraint or not. Second will be the moment about the axis x. So that is our restraint with respect to the theta 1, and second will be third will be with respect to the moment about the second in plane direction of the given grid, and that is the restraint theta 2 of the given system. So we typically define these as the input parameters for the node system. When we go to the member system, we define the same way, that for the member, say any of the member I, what are the individual joints, say the joint j and k of the given system, individual member area what is defined, then the elastic coefficients of the given member, then we define here the I and j values of the given system. As we said that when the twisting is taking place in the given member, so if this is say any given member, if the moment is corresponding to the twisting components, so we require the second moment of area about this axis x of the given system. So you can call it as either Ixx, or we define it as a polar moment of inertia or a j in the given system. And in the same manner, when the flexure is taking place about this axis, the second axis y of the given problem, the member will typically like to bend in this way. So due to this bending component on the given system, we describe the second moment of area about this axis yy itself. So we look for either Iyy or Ixx in the given problem, which are the second moment of area required for the flexural and the twisting cases. Length of the member, cosine alpha and the sine alpha of the given system can also be defined once your coordinates in the given xy plane are known to us. With this idea in mind, we go ahead with the stiffness evaluation. So as I already said that we have these 6 degrees of freedom which are located in the member coordinates. So at each of the point we define the individual contributions of the stiffness contribution. Now these stiffness contributions are defined in the local coordinate, which means that I can say at the beginning I can define that this is a fully restrained system. As a first degree of freedom, I just apply the twisting component over here, which means that some amount of twist will be defined or given to this member. Corresponding to that, the amount of force which is generated, that is Gj upon L in one of the direction, and in the opposite direction it will be, or in the second node it will be opposite. So this is minus Gj upon L. While we are providing the twisting in the given system, only the twisting moment will be generated. The other flexural and the transverse deflections will not be available in the given system. So that is why the remaining components are 0 for the given problem. As a second case, we bring the same member fully kinematically restrained, and now we apply the second degree of freedom in the given problem. Now the second degree of freedom is the amount of the moment which is provided with respect to the direction y in the given problem, which means that I need to apply the unit rotation in the given problem. So with this unit rotation, if I provide the system, so the system will bend in this manner. So based upon this calculation, I can now evaluate the fixed end moment and the reactions in the given system. If you do this calculation, you will get these values as 4 EI, and we already said that I value will be now about the axis y in the given system, 4 EI upon L, and this value will be 2 EI y upon L in the given problem. Similarly, we can also evaluate the amount of the reaction in the given system. So the vertical reaction in the given system can be evaluated. We must understand that these reactions are normal to the given plane now. So they will be identified as 6 EI y upon L square at both the ends of the given system. And we substitute these values corresponding to the node 1. We have the first component 0, the second component as 4 EI upon L, positive in the direction, the third component as a component which is downward, I think. So this component I think will be coming out to be downward over here, and this will be coming out to be upward in the given system. as per the rotation sign convention the way we have defined, I think I'll just switch it. So, as a second degree of freedom, we have defined this as the position of the positive rotation in the given system. So, if we define the positive rotation in this manner, which means that the member will bend in this way. So, this is the possible rotation which the member will take, and that is where the member coordinate will bend in this manner. And with this idea, we can evaluate that these will be the directions of the moments, which are 4 EI y upon L and 2 EI y upon L in the given system. And once we get this value of the moment, we can get the value of the reactions in the given system in the vertical direction, and they will come out as 6 EI y upon L square, and this one will be again 6 EI y upon L square. So, this one is negative, which is at the node 1, and the second one is positive, which is at the node 2 or the node k of the given system. So, with these values we can evaluate the response of the given system. As a third measure, we typically go with the system again, both the degrees of freedom restraint, and now we allow the third degree of freedom to appear. So, this is the translation in the vertical direction. So, the support moves from this position. This is how we define the given deflected shape, and corresponding to this deflected shape, if we get the value of the moment in the given system, we get to know that the moment directions will be like this, and the reactions will be applied in the given system in this manner. So, we got to know these values evaluated: 6 EI upon L square, 6 EI y upon L square, and the value of the reactions 12 EI y upon L cube in the given system. So, I have just taken these values as we have done all these exercises multiple times in the given course. So, using these values now I can again reproduce the values. So, the first value is 0 because there is no horizontal twisting moment in the system. The second one, if you get the value of the moment, if you put with the right hand curl rule, the amount of the moment 6 EI upon y Iy upon L square is located in this direction, which is opposite to the positive sign convention. So, that is why it has been provided with the minus of 6 EI y upon L square. The vertical force is positive in the given point. So, this is 12 EI upon L cube, and similarly the other two values minus of 6 EI upon L square and the vertical force minus of 12 EI upon L cube can be defined. In the similar manner, we can also go ahead with the degrees of freedom at the node 2 and calculate their values, the stiffness contributions of the given system. Once we have these stiffness contributions known to us, we evaluate the stiffness contributions in the global directions. So, to evaluate the global direction stiffness calculations, we now realize that we need to have a transformation relationship which will convert the local coordinates degrees of freedom to the global coordinates. To do so, we realize that this is the local coordinate of the given system, local member axis, corresponding to which we have these defined directions of the given system, and these are the global directions of the given system. So, if at a point I just bring all these values together, I say that corresponding to the directions of the given system. So, this is the global direction of the x, this is the global direction of the y, and this is the global direction of the z. One must understand that when we are talking about the grid system, the most of the calculations are defined in the horizontal plane of the given system. So, that is why I have defined the x and y axis in the horizontal plane, and the z is the normal plane to the given surface. So, now at any point if you locate the given, so if I just locate it over here, at this point corresponding to the member direction, the individual degrees of freedom were defined with respect to 1, then 2 and 3 in the given system. So, these were the 3 degrees of freedom which were located in the plane of the grid, now in the local member coordinate. Now, if I just want to convert it in the global coordinate, I realize that this is the first one which is along the direction x, second one the moment about the axis y, this is second, and the third one which is the direction normal to the z, and that happens to be the same in the given system, right. So, with this idea, what I realize now that the axis z of the given problem is remaining same, because as we are only changing the members with the different orientation. So, we can have a possibility that member can either lie in the same plane or member can have some inclination in the given plane xy, but at any point the normal to the given member axis is always along the z direction of the given problem. So, this will give us a kind of, if I just define the rotation matrix of the given system in terms of the three values which are the so if we have defined the values with respect to say theta at the for the member at the joint, yes, I can define with the joint j. Then similarly theta, this is with respect to the direction 1. Then similarly theta for the member coordinate at the joint j for the second degree of freedom direction, and then delta, which is again for the member at the joint j in the member coordinates, and this is the third one. Now what we realize with this part, that all these three values which are with respect to the rotation theta 1 and theta 2, they are within the same plane and they are just translating in the given plane only, which means that either I am defining for this grid member. So if I just define a grid member in the system, like this being the coordinate system, this is say one of the member, this is second, and this is say the third member. Say one of the member is in the same direction of the x coordinate. So for this the x direction will come out as the global directions of the given system. The second member, which is this one, for this the local directions or the member directions will appear like this. So the moment which we will define at any point in this given member will be appearing along the same two directions of the given system. So at any point the contribution which I am going to look for the moments in the local and the global direction, they will simply transform like what happens in the simple 2D plane. If in a 2D plane I go with the condition and the x and y axis, and I bring the new axis as x prime and y prime in the given system, so I can simply give the relationship that x prime and y prime is defined in terms of the original x and y in terms of cos alpha sin alpha minus sin alpha cos alpha, this relationship. Now we can understand that if everything is happening in the grid plane only, so in the grid plane whether you go with this direction of the moments or you just bring some new directions which are again in the same plane but located in two different directions. So one can consider like that this is a plane of the grid in which, so like this is a plane of the grid in which there are two members. Like rather than taking the moments in these two directions, I can just bring the direction like this. So now the moments are being taken along these two directions. So the rotation axis will become same, whereas for the z direction there is no change, because with respect to the theta corresponding to the direction z, I realize that the normal axis remains same all throughout. So it can be defined in a simplistic manner now, that theta with respect to, so I'll just move it. So theta with respect to the given coordinate system with respect to the local axis and the with respect to the global axis can be correlated by a standard rotation matrix, and that appears same: cos alpha sin alpha 0 minus sin alpha cos alpha 0 0 0 1, right. 0 0 1 typically describe that the delta of M3, the z direction deformation which you are defining for the given member or which you are defining for the given global system, both are in the same directions, whereas what we define for the individual member coordinates, the two moment directions 1 and 2, when we come up with the global directions of the system, they are within the same plane but with the different orientation. So that is why the same 2D representation which we were doing earlier will be utilized. Now probably it makes a sense that why did we use the numbering system with the first 1 2 being the moments of the system, because we understood that that is in the same plane of the grid. So it is in the same xy plane, so every time I can just bring the difference. So if this is the member coordinate, the two moments which I am actually looking for are in the same plane of the given system, they are not changing in the given plane, whereas the third one which is normal to the given system, that is the same direction 3 of the given problem. Okay. So with this idea in mind, we realize that the individual rotation matrix which we described earlier for the given frame system can be utilized again. Only difference is that the first two are the degrees of freedom with respect to the rotations, and the third one is the translational degrees of freedom. In the same manner, we can define for both of the part, the member and the structural components of the given system. Once we know this part of the rotation matrix of the given system, we can easily convert our member forces in the local and the global coordinates, and we can also get the stiffness matrix of the given system from the individual local member coordinates to the global matrix. Now, of course, this is done for individual single member only. Now, once we are able to do this much part of the system, we understand that the remaining part of the calculations will be similar what we were doing for the frame system. So, we will quickly show that how do we do the remaining part of the procedure. So, this is a problem for the truss, the grid system, in which the load which are directly active at the joints can be located. So, we come up with each of the joints, say if I call it as 1, 2, 3 and 4, and I define that at each of the joint where the degrees of freedom are located. So, at the node 2, I consider that at the node 1 there are no joint loads. So, this is 0 with respect to the degree of freedom 1, 2, 3. With respect to the node 2, there are 3 degrees of freedom 4, 5 and 6, and in the degree of freedom direction 4, I have a twisting moment, say let me call it as a M1. So, this value is available. Similarly, when I go to the joint number 3, I realize that this is the direction 7, this is 8 and this is 9 of the given system. Of course, here it is a moment and there is it is a translation. So, with respect to the 7, 8 and 9. So, for the node 2, I have only one of the value M1, remaining 2 are 0. For the node 2, along the 7 I do not have any moment, along the 8 I have a moment, say this is M2, and along the 9 I do not have any translational or a vertical force in the given system. Similarly, when I go to the node 4, I do not have any forces there. So, I simply put corresponding to the 10, 11 and 12, the values are 0. As a next step, I go to the calculation of the member contributions. As a load is active on the given system in a transverse direction, we calculate the reactions of the system. This reaction will be in the, so you can consider now that this is a member, the member is in the given plane and the load is active on the system which is in the vertical, the normal to the given plane of the system. So, this is what we have identified, that if the system is in the xy plane, the load is active in the z direction of the given system. So, this is the load direction corresponding to which we can evaluate the fixed ended reactions. Once we get the fixed ended reaction in the local coordinate, we just convert them into the global coordinate of the given system. Once we have available set of forces as well as the stiffness matrices in the local or in the member system, we can now convert the overall global stiffness matrix as well as the load vector. We identify that for any of the member I in the given system, there will be 2 of the joints, say J and K in the given problem, and for these 2 joints we have now 3 degrees of freedom defined at each of the joint, out of which 2 are the moments and 1 is the translation. So, now we label these degrees of freedom as, this is 3j minus 2, this is 3j minus 1 and this is 3j, this is 3k minus 2, this is 3k minus 1 and this is 3k. Finally, we end up with these values and we locate it in the same manner as we did for the plane frame system. So, 3j minus 2, 3j minus 1, 3j and 3k minus 2, 3k minus 1 and 3k. So, these are the individual rows where we will try to put the contribution of the matrix of the local contribution of the member system. Similarly, this will be the S2, this will be the S3 and this will be the S4 component of the given system. The idea is that the overall stiffness matrix which has been evaluated for the individual members in the global coordinates can be placed into 4 places in the global assembly, and that will be defined by the individual rows and columns in the order of 3j minus 2, 3j minus 1, 3j, 3k minus 2, 3k minus 1 and 3k in the given system. We do the same for the loading system also. We define the load vectors and place it in the similar positions of the given system, that 3j minus 2, 3j minus 1, 3j, 3k minus 2, 3k minus 1 and 3k in the given system. Once the loading vector and the stiffness matrix is assembled, we rearrange the given system in the order of the free and the restrained degrees of freedom, and once the free and restrained degrees of freedom are arranged, we define the system for the final solution and evaluate the response of the given system. So, this procedure is same as what we did earlier for the plane frame system also. With this, we stop over here. We have briefly seen the standard procedure of the grid structures. Important point is to note that what is the transformation matrix for the given system and how do we define the standard stiffness matrix for a grid system. The remaining part of the procedure remains very systematic and similar to what we did earlier, and this also remains one of the important aspect of the stiffness method, that why it is suitable for the computer implementation. With this, we stop over here. Thank you everyone.